So I'm going to talk about river herring, and it'll turn out to be about alewife, and I'll explain to you why I'm using the term river herring. And I call it the once and future fish because this is a fish that once was very abundant and we hope might be so in the future. My co-author, Dr. Theo Willis, is also here. He is also an alewife expert, and between the two of us, hopefully we can answer your questions. He also helped put this talk together. So I use river herring because there are two species of fish that look almost identical. Can you tell the difference? I could barely, but you can sort of. And then, unfortunately, they also hybridize. So the alewife tends to be a little bit deeper in body and a little bit bigger eye relative to its head. The blueback tends to be a little bit more riverine-ish, not as deep, and a slightly smaller eye. And to really know, you have to open them up and look at the lining inside the body. This lining is black, this is pale or white, but then they hybridize and they look half and half anyway, and so. But anyway, here we are, river herring. I'm primarily going to talk about alewife today, and I'll tell you why. And that is because, although both of these fish have a very similar life cycle, alewife spawn in lakes, whereas blueback herring will spawn in rivers, large rivers, or also lakes. But alewives are the most dominant species here in Maine. So this is their life cycle. And it's a pretty interesting one in that they're primarily, or many people think of these fish as marine fishes. So that they spend their adult time in the Gulf of Maine. They go all the way up to the Gulf or Bay of Fundy. They go down to Cape Cod. So they're way out there. But every spring they come in to spawn. They go back to their natal rivers or lake systems where they were born, swim upriver, leave their eggs in the lakes, and then turn around and go back out to sea. So they're not like salmon. They don't all die when they get up there. They go back out to sea, and individuals might spawn again maybe 3 or 4 springs in a row if they don't get eaten out there in the ocean or caught for bait or something like that. An individual might lay 30,000 eggs, most of which don't make it. Those that do spend anywhere from a month to 3 or 4 months in the lake before they migrate out. They spend a bunch of time in the nearshore marine and estuary habitats. By about 2 years old, though, at the end of their 2-year-old summer, they're heading out to sea. And then they'll come back at age 3 or age 4 for their first spawning event. So it's a pretty complex life cycle. This is the range of alewife. It's very similar to the blueback. And there's 2 important things I want you to see here. One is that native range is both in the marine system, but also up into the interior parts of all these states because of running up the rivers. So that's one important thing. And the other thing to note is that you'll see a whole bunch of introduced alewives up in the Great Lakes in particular, and a bunch of inland lakes, usually because they were introduced as food for fish, or in regards to the Great Lakes, they made their way up through canals up into the Great Lakes and then were landlocked. So if you do a Google search for alewife, half the information you'll get will be about alewife as an invasive species. So be aware that here in Maine, they're quite native and have been here for a long time. And it actually wasn't until maybe about 6 or 7 years ago that a Google search would pop up information about the fish in their native range as people have become more familiar with them. So this is their historic distribution in Maine, and I think what's really important is to note how far up these rivers these fish would swim. So they are really, really interior. So they're bringing all this marine productivity way up into the state, very, very far. Unfortunately, their distribution today is much abbreviated relative to the historic distribution. So you can see mostly just coastal rivers, and then getting up into the Kennebec and up into the Penobscot and up into the Kennebec. And a lot of this these ranges now have been due to a lot of work from the Department of Marine Resources and Inland Fish and Wildlife and lots of others to open up passage up these rivers. So you might ask, why the push to restore alewife? Why is it that maybe 10 or 15 years ago in a lake you might have never heard a thing about alewives, and now you hear about alewives all the time? Why do we care? One of them is that they've experienced an extreme drop-off in their numbers at sea. So these are catch rates, not actual numbers. And you can see that things sort of sputtered along in the millions of pounds of fish harvested until you get into the 1940s through the 1970s, when there was a huge offshore intercept fisheries. And it was after that fisheries event that their populations crashed, and importantly have stayed very low in most places except Maine. And in many places, the restoration efforts that are going on in Maine wouldn't get much of an effect because they're being caught offshore still. But our fish do okay. So they were proposed for listing under the Endangered Species Act in 2013, which was declined. So they're not listed, but they are a species of concern at this time. So there's a lot of reasons for wanting these fish back. One is they do have an economic impact. This is the Benton Falls Dam harvest. There's 16 licensed harvests around the state at this time, and about 5 or 6 more that people are working on bringing back online. The nice thing about these harvests is it benefits both the harvester as well as the town that gives out the license. So the town gets a nice little small but significant revenue source. This all goes primarily to the lobster industry. So this is a spring bait, a local bait, which can be very helpful in the early spring. They also can provide food for people, as was implied earlier. They were that sort of early spring protein source coming up the rivers, reliably up the rivers. So people used to smoke them and salt them, and the law on the books where you could get a free bushel or two is still there, although it's modified a little bit now, but it's still on the books. And that's because this was starvation food. This was for widows who had just barely made it through the winter. They didn't have someone helping them out, and they were starving and needed some food. So this is what these were. If you've ever had a smoked alewife, they're actually pretty good. You should give it a try. And finally, they're responsive to restoration. I had mentioned earlier that they come back to where you introduced them. And when you reconnect their habitat and allow them up into their historic spawning sites, you actually get fish back, which is a pretty good return for your money. And what's interesting is it's one of the only fish that's considered a marine forage fish that we actually have direct impact on their spawning success. So Atlantic herring, we can stop fishing for them, but we can't give them more access to their spawning grounds. But these guys, we can actually give more access to their spawning grounds. So it turns out that if you give them more access to spawning grounds, you get a lot more fish. These are data along the bottom of number of adult spawners put in various different ponds in the Penobscot watershed. If you take an adult spawner that's ready to spawn and you put them in a lake that they've never been in before, they go ahead, they spawn, and their offspring come back 3 to 4 years later. So it's a really easy way to restart a run that may have disappeared in the past. So these are the numbers that have been stocked in the Penobscot watershed from 2010. And these are some of the fish passage efforts that have been done over that time, so a lot of work going on there. And this is the type of returns you start to see. So here we're well under 10,000 fish or so coming back at the VZ Dam way back in 2010, and now well over 1 million fish and rising. So you get a really good payback for your money, and it's one of the few restoration efforts that is a pretty good, feel-good story. Unfortunately, it works the opposite too. So if you take away access to the habitat, as happened in the St. Croix River between 1985 and 2000, these blue bars are the amount of spawning habitat available for alewives in the St. Croix River watershed. And through a series of closures of fish passages, the spawning habitat dropped off, and you see a very dramatic reduction in the number of fish. So that goes either way. That's a big story, by the way, which we won't get into. Another reason to restore these fish is that they're a food for everyone. So we call them a forage fish when we're talking fisheries. And that is that everything eats them, from your bass and your mammals and your birds down to your cod that, of course, people are very interested in reestablishing in the Gulf of Maine and nearshore marine. And so this is a great forage fish for those organisms. And a lot of things eat them that you would never expect. Like mink and other, lots of organisms, anybody who can get one. So here's a largemouth bass, or smallmouth bass with a tail of an alewife, a full adult alewife right down its throat. And here's a bass where we stole its dinner, we flushed its stomach, and it had an alewife in it. So this happens all the time. This was in the Kennebec. This is a plastic worm. But anyway, so they eat a lot of alewives. Essentially, anything will eat an alewife that can get it down their stomach. So the question I really want to come to today, after convincing you that this is a great fish, this is usually the question I get when I talk to people in lake associations is, do alewives cause algal blooms? And you might say, oh, well, I never thought of that, or maybe this is a pressing concern in your lake. And so I'm going to talk a little bit about what's going on there. There's two mechanisms by which you might expect algae or phytoplankton to increase when you have alewives in the lake. One is, because they're coming from the ocean, and there's a whole lot of them coming up, you might think that they're bringing in nutrients from the ocean, especially if some of those alewives die when they get up into your lake. So that's one mechanism. And the other is that alewives are very efficient zooplanktivores, and zooplankton eat algae. So if you take away the organisms that eat the algae, then maybe you'll have more algae. So those are sort of the two mechanisms, and they interact as well. So what I'm going to talk about in the next few slides is sort of where we are now with this understanding of this sort of system. And the reality is there's probably about 5 researchers right now that I could name who are in the middle of a master's thesis or a PhD thesis that pertains to this question. And so what we're really doing as a scientific community is gathering a lot of information about this question because it's complicated, and hopefully I can convince you that, at least if nothing else, convince you that it's complicated. So when we're talking about nutrients, what you need to think about from a fish's perspective is, imagine that fish is a packet of nutrients. It's full of nitrogen and phosphorus, just like you and I are, but it's moving across habitats from the ocean up into the lake, and also from the lake back to the ocean. So our adults come in, they're full of nutrients, some percentage of them die. This is a big question, we really don't know. When they die, they release nutrients into the water. But what if they died because they were eaten by a bass? In that case, most of their nutrients are incorporated into the bass, not released into the water. So you can imagine there's a lot of unknowns there. The nutrients can help grow more algae. And then these adults also turn around and go back out to sea. They eat a little bit while they're in the lake. They take that freshwater nutrients back out to sea. Then their juveniles spend all summer growing big, 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 big. And then they all leave, and also can represent a net export of phosphorus out to sea, because they're taking all those freshwater derived nutrients and taking them out with them. So we sort of think of it this way. Let's see if this makes sense. So on my graph that has actually no data in it, here's the amount of phosphorus in fish, and here's the number of adult spawners that actually enter the lake. So our assumption is that the more adult spawners that come into the lake, the more adult alewives die, just because you're bringing in more fish, and that means there's more phosphorus coming from fish in the lake, from those adult alewives. At the same time, the more adult spawners that come into the lake, the more young of year or baby fish that you get, right? And it turns out that early on, when you have not a lot of adult spawners, there's a lot of material or productivity in the lake, lots of things for all those little baby alewives to eat, and so there's many of them are very high biomass. It also seems, and again, this is part of that research in progress right now, that most lakes have some kind of cap on the amount of baby alewives they can produce, or the biomass, either lots of big ones or many little ones. And that just has to do with how much productivity is in the lake itself. So you get this sort of curve where when you get lots and lots of young of year, lots of spawners coming in, you kind of max out at some point. And so the thought is that as long as there's lots more young of year biomass than the adults coming in, that you're actually going to have a net export of phosphorus. As long as you're producing lots and lots of little alewives for the amount of adults that are coming in. But as soon as you get up into this upper part of the graph, where you're just no longer producing any more young of year, at that point, the more adults you add to the lake, the more spawners, the more phosphorus you're probably bringing in. So the take-home message is that whether alewife are bringing net phosphorus into the lake or taking it out probably depends on the relative numbers of adult spawners versus young of year, just relative numbers of adult spawners. You will be hearing more about this as several master's and PhD theses come to fruition. So let's talk a little bit about the other effect. And the other effect is eating those zooplankton. What's next? There we go. So if you were going to go out into a lake that had sea-run alewives in it, this is a catch that was made in August in Highland Lake in Wyndham. Highland Lake has a very small outlet stream, so you tend to get alewives staying in the lake for much of the summer. And here they are. They're only about an inch long, and these fish are throughout the pelagic zone, the middle of the lake, in the top 10 or 15 feet of water, eating zooplankton. That's what they do. And so they actually found fish of the same size throughout the entire summer, because what happens is, as they get a little bigger than this, they're too easy for predators to see, and they migrate to the shore and they start swimming around in schools in the vegetation on the shoreline. But we do know that alewives have a big impact on the zooplankton community. So this is a very simple graph showing the mean length of zooplankton before alewives were reintroduced and after in the orange. So you can see early in June when the alewives just arrived in the lake, it's about the same. But as you progress through time, the mean size of zooplankton decreases the year that alewives were present in the lake. This is a pattern we see in every alewife lake out there. And it's just because alewives are such excellent zooplankton eaters. So you see reduction in the mean size of zooplankton. And you also see some changes in the dominant zooplankton species. So you go from larger zooplankton to smaller zooplankton species. Okay, so I should be getting close to time, right? Am I over? Okay, so do they in fact cause algal blooms? Part of the problem of everything that I've discussed so far is that it all happens in the context of the nutrients that are already in your lake, right? So if you have a lake with lots of nutrients coming in, it might be that the amount of nutrients brought in or taken out by alewives is nothing compared to what else is coming in. So it depends on how much phosphorus is coming into your lake. It might depend on how much phosphorus is already in the lake in terms of internal cycling and how quickly the lake water is flushed out so you get new, cleaner water. I have heard a variety of commentary from people who live on lakes that have alewives. Everything from, oh, we see no effect at all in terms of whether there's algae or not, or that you might hear that people will see short duration, sort of low intensity blooms that clear up once the majority of the juveniles leave the lake. And then there are even some lakes that alewives have been reintroduced to that have also seen a reduction in phosphorus, except like in Sebastopol and Weber, but they're always accompanied by other measures that are happening at the same time to reduce phosphorus. There's always something going on in the background, like reductions in erosion and things like that. So certainly in this case, the alewives didn't prevent the increases in water quality, but they couldn't probably do it all by themselves. Unfortunately, what we don't have is a lake out there where they've been reintroduced and we have nothing else happening. So there's always something else going on. So no one ever just introduced them and then did nothing else to the watershed to see what would happen. Thus far. That would be a great experiment, but it hasn't happened. So the question is, can this be a win-win situation? With the reintroduction of alewives, you get more wildlife, you get options for harvest, you get more marine forage fish, you might get phosphorus removal. But it seems like if you do have a phosphorus problem in the lake, you can't assume that alewives could take the phosphorus out. You have to continue with phosphorus control measures. And then the thing that I would like to leave us all with is this idea that if alewives are reintroduced into your lake, The important thing is to actually be collecting data so you know what's happening. And there's two critical pieces of data. One, water quality, and one is to count the number of adults coming into the lake, because that's the number that we need to be able to estimate the amount of phosphorus coming in once students put their work together. Okay, I'm going to stop there and open up for questions. Okay, John.
I'm wondering about your count of the spawners. The data you get eventually, will you be able to further or more closely control the amount of harvesting? Right now on Orland River, there's a 4-day per week or was in the season harvesting. Will that drive your control of that or suggestion of control?
So the question was about once you know how many adult alewife spawners are coming in, what might you do with those data? So we count alewives coming into spawn for a lot of reasons. Part of it's just population numbers to know that we've got the returns that we want. But the other is also because the thought is that in some lakes you might want to limit the number of adult spawners that come in if we think that phosphorus is an issue in that lake. So if you're counting them coming in, you can start playing around with, well, what if for a couple of years we drop the numbers down? How does the lake respond to that? What if we increase the numbers? How does the lake respond to that? So there's possibilities for doing some adaptive management, but the way you can only do adaptive management if you have data to start with.
Is there a difference in the food web effect of the adults versus the young year? Are they eating on a different?
Good question. When the young of you are very small, they're eating really little stuff like rotifers. The adults will eat both larger zooplankton as well as benthic invertebrates, insects that have fallen from into the water surface. They're pretty opportunistic.
Do they go after any of the mussel?
Oh, Glaucidia? So the question was, do the adults eat the mussel Glaucidia? They might pick them up accidentally, but they're not targeting them. Yeah.
It'll be a real boon if your students can show that there's net export of phosphorus, no doubt. On the other end, not going in, what about the marine nutrients, compounds, the pigments? I've talked to folks that feel that that's very important to get to sport fish in egg quality for sport fish when the alewives come in early in the spring. They're consumed. Is there anybody that's tracking through to see if there's specific targeted pigments or marine compounds that could be tracked through to see if that would be a further reason for the support behind the reintroduction of alewives into watersheds?
So I think what you're asking is, are there, can we track the materials in the alewife and see if it's coming into getting into the sports fish? And you can actually, you can use stable isotopes. And we've done that before, and you do see an increase in marine-derived stable isotopes, which is, we could talk later about the details of how you do that, but you can actually pick that up.
How about disease? Has there ever been, have you ever seen an introduction of disease that would come through alewives as the vector?
Not in a sea-run situation. Good question. Oh, yeah? All right.
Thank you.